Hi, I'm Graham Jones. I'm one of the lecturers at City of Bristol College. I'm delivering the manual machining limits and fits unit for yourselves. So, start off with the machining process. There are two basic machines for this. There's the milling machine, which produces square items, and the lathe that produces cylindrical items. This is an image of a milling machine taken in City of Bristol College. So it's quite a large machine. The smallest one I would say is probably 6.5 foot, and then going up to the very big one, which photographed, probably getting on towards 7 foot high, to the very top of the head here. So the directions of movement on a milling machine. You've got the x-axis, which is left and right. So left is x minus, and then going towards your right would be x plus. You've got the in and out of the bed, which is, as it goes away from you, is x plus. As it comes towards you, is y plus. As it comes towards you is y minus. And then you've got the up and down, which is z plus as it rises up, and as it goes down then is z minus. So z plus, z minus. Normally have a datum point on a drawing, so you'd use that drawing point as the datum edge for all of these measurements to come from, and then the surface of the material would be your Z minus going down into the material, and then Z plus would be going up and away. So we're going to stay on the milling machine until we've gone quite a way through it, and then we're going to move on then towards the lathe. Staying on the milling machine, we've got a selection of different cutters that, if circumstances were different and you'd be able to come to City of Bristol College, we would be using these cutters to produce the artifact that you would be manufacturing. So just a couple of small images, and then I'll show you, I'll go into a bit more depth on these cutters. So this item here is a face cutter, and it is bolted into the head on the milling machine, and this then rotates and removes the material. So there are two variants of these. There is a high-speed steel one. They can be resharpened. They tend to be quite expensive to get them resharpened, and more commonly in engineering they use the tungsten carbide tip version, which is pictured. As you can see where my pointer is, there is little torque screws, and the operator of the milling machine then, as the cutter wears, the operator then can stop the machine, replace these little tungsten carbide tips. It's relatively quick. However, the price of a cutter is quite expensive. The tips are not that expensive, but it's still quicker in a turnaround side than having a high-speed steel cutter for the size of these cutters. So these cutters vary from about 15 centimeter diameter going out to The largest at City of Bristol we have is a 30 centimetre diameter. So there's quite a range in diameter for the size of the cutter, and then it varies then the amount of tips you would have in these. So ranging from, each of those tips is about between £5 and I've seen them going up to about £30 a tip. So it can get quite expensive, but then it's cheaper than having a high-speed steel one. So now we're moving on to the end mill. The end mill is, so if this is your material, an end mill would come along and cut the end of your material. So come in and cut along there. The most commonly high-speed steel. There are tipped ones. I've never really got on with them, but they're more of a specialist tool. The high-speed steel ones are relatively cheap and easy to replace. So the one that's pictured here has 4 teeth, and you would, when you're calculating the speeds and feeds, this would need to be taken into account to make sure that you've got the right feed rate and speed rate for the amount of tips. I'll go into the speeds and feeds later on in this presentation. So, slot cutter. Slot cutter is used, as it states, to cut a slot. It's also used to drill into a hole with an accurate measurement. It would cut slightly different to a drill because of the flat bottom on there. So you could then machine a blind hole to a flat square bottom blind hole. The flutes on these, that's the spirally bits, are closer together than the previous slide. So that's the easy, quick way to distinguish between an end mill and a slot cutter. What you need to take into account with a slot cutter is the length. So if you've got a longer slot cutter, what can happen is it can actually bend as you applying pressure. So you would have to step and cut down in steps, not to get too much bend in the cutter. And when the cutter actually bends, your hole diameter would be inaccurate because the cutter would actually wander as it's going down. And so if it's cutting, rotating down and cutting, and then starts to wander, your hole will end up going from, say, a 10mm hole, and it can open up as much as 14-15 millimeters. So you get a 5mm difference by having a small diameter, a 10mm slot drill with the wander. So just bear that in mind with your machining in the future. Right, so we're on to the lathe. This is one of the lathes that we have at City of Bristol College. As I stated earlier, produces round items. So you actually put the workpiece into this part, the chuck, and then the chuck rotates the material that you're going to manufacture. The cutters all stay still, and I say stay still, they don't rotate, and then they move into the rotating material. So, directions of movement on the lathe. So, left and right is your Z, and then from you going backwards and forwards would be your X-axis. So you'd have the material sticking out, and normally the end of the material would be Z0, and then going into the material would be Z minus, and then however much you're traveling in. And then, so if this was your round piece of bar and you touched on this end here, would be X0, this would be Z0, so X0, and then the further you go into your material would be X minus X, and then the further you go away from your material would be plus X. So, turning tools. It is a wide variety. Some of the stuff can be custom ground for custom profiles that you're machining. These are the three that, if you were able to come to City Bristol, we would be demonstrating with. So I'll go into these cutters and explain a little bit more. So we've got the left hand knife tool. This is back to front, this photo, but I took it so you would be able to see what the cutting angles actually look like. Down here we've got a tungsten carbide one. It's exactly the same to use as this one here. Most of the ones we use are high-speed steel, because you would have a high-speed steel bar that would be ground to the correct cutting angles. Those cutting angles then, if that tool got worn or even was fed into the material too fast and it took a bump, myself or the technician can very quickly grind that on a pedestal grinder to be back to a working cutting edge. The trouble is with the tungsten carbide, if it takes a bump, it can actually bend the cutting bar, and it takes longer to check that these cutters haven't been damaged, are going to cut square. The tip of the cutter tip on the end, the little tiny gold bit, is the actual cutting material. We've got to check that that is geometrically square to actually produce items correctly. So that's it actually on a lathe. That's the material there, and then that's the chuck that is holding the workpiece. So next then we've got a parting off tool. Back to front again so you can see the cutting edge. The image down the bottom is it actually in process, so you can see it actually being used. The tools in engineering, like you probably gathered with a milling one, the clue's in the name, is for parting the items off. So if you were mass producing these cylindrical rings for an item, then you can machine the bar down to the diameter and then just part them off at the distance that was required on the drawing. It also can be used for cutting grooves for rubber O-rings, oil seals, stuff like that. But normally the tool would have to be ground slightly different, so it's not a square edge, it would be slightly round, so the O-ring, the rubber ring, then could go into that and sit tidy. The 45-degree cutting tool. So this is a bit of a custom grind tool. So these angles here are set ground to be at 45 degrees to the material, to this cutting edge, to the bar edge. So this can go in then, as it's shown on this diagram, this photograph, that it will go in and can either cut 45-degree chamfers, or we use it to deburr the material. So a burr is a sharp edge created in the cutting process. These edges can be very sharp, so we use this tool just as a safety tool, and would take that sharp edge off the cutting the material, so then it is safer for you to handle. Right, the use of coolant. Coolant is basically a mixture of oil and water. We can't just use water, as water will speed up the corrosion process. So it's at a ratio, it varies machine to machine and coolant brand, etc. So it's a mixture of oil and water. It's normally a white colour. Some machines have a specified added chemicals which will create basically a dye in the coolant, and I've seen green colours, purple colours, weird and wacky. The most common you would come in contact with would be white. So coolant is used to reduce the thermal expansion in the cutter and in the material. So coolant is used both on the milling machine and on the lathe. And it's also used to lubricate the cutter as it's rubbing up against the material, so it's rotating. You're going to get friction, and this then will lubricate and reduce the amount of friction and therefore the heat generation. So if your cutter then expands with heat, it could create a hole out of tolerance. Also, the material, you don't want that expanding, because when you come to measure it, it could have expanded and you go in with vernier calipers, etc., and it don't work. Cutting speed is calculated by pi times diameter times spindle speed divided by 1000. That'll give you an RPM. Spindle speed then is calculated by the cutting speed divided by pi divided by diameter times 1000. The feed rate is spindle speed times feed per tooth times by number of flutes. Feed per tooth is F times S times N. Feed times spindle speed times number of flutes. So that's how engineers would work that out. The spindle speed can vary due to material being cut, so different densities of materials. It also, you need to be aware of things like high-speed steel cutters will cut at a slower speed than a tungsten carbide due to the density of that material, the cutting material. So when you're looking at what tools you can use on a lathe or a miller, the tungsten carbide ones on a mass production scale, you can have higher speeds and higher feed rates because the material is harder than the high-speed steel. With that, you can reduce the component manufacturing time, so therefore you can make more components in the working day. So things like that need to be thought of when you're picking cutters. When you're coming down to making one-offs, there's not really a lot of difference, but when you're making thousands of, you can squeeze in another 100 or so in the same time scale, in the time scale that you would make 1,000 of with high-speed steel cutters. You can then make, for example, 1,100 in the same time scale with tungsten carbide tip tools. Right, down to surface finish now. When a component is machined, the speeds and feeds, as on the previous slide, will affect the surface finish. So if the feed rate is high and the spindle's rotation speed is low, you're going to end up with a rougher surface finish. So there's quite a crude, rudimental, you literally use your nail and you run it along that little chart, and then you go pick up your item, do the same and compare the two. It's quite crude. When it goes to the inspection labs, normally if you're manufacturing on a mass scale, they would then have a needle, they would put your component on, and the machine then would drag this needle and measure this extremely accurately. So you can see the rotational marks on this as it goes along. And then this further over towards the right on this chart, this is the ultimate, the smoothest possible finish you would get on a manual machine. Most of the components that the components that you would be manufacturing if you were able to come to the City of Bristol would be looking around this sort of level, which is not quite mirror, but it's very smooth. You wouldn't be able to feel the lines, but they would be slightly visible. So those lines then correspond over here, and then that is down to the roughness spacing. The waviness is the larger indentations. Indentations. So this is magnified on quite a grand scale for you to understand it. The roughness is actually measured by the depth on how deep the little grooves are. And like I said, you can reduce that by slowing the feed rate of the machine going across, so sometimes it's a little bit of trial and error with manual machining. So you could speed up the spindle, for example on a lathe, you could speed up the spindle and slow the feed rate down, because if it's going across like this and the piece is rotating, that's how you're going to get your grooves, by it's moving too fast to cut evenly. Or you can increase the spindle speed and slow this down, and then it'll cut perfectly as it goes over the material. So now into limits and fits. So the task that some of your classmates have carried out in City and Bristol, so over the 2 weeks, the week one, they would have made something on a lathe. It's a little round piece of material, 2 different diameters. So, and then week 2, they would create a square block, and then this peg would have to fit into the holes. So the idea of this task is that they would make a 20 millimeter diameter bar, and then drill using a slot mill a 20 millimeter hole. Now the tolerance on that was 0.12 millimeters, and if they made them the round bar at 20 millimeters, the hole at 20 millimeters, which is set by the size of the slot drill, the two components wouldn't actually go together. If they took it the diameter of the round bar slightly, we're talking 0.02 of a millimeter, they slot together lovely and everything is perfect. So it just gives them appreciation that, especially when you're designing on CAD, that the components can't fit. A 20 millimeter bar will not fit in a 20 millimeter hole without force, which I'll go into on the next slide. So we've got the selected ISO fits, the two British standards on this chart. I've picked out this here for a 35 millimeter bar. It's nice and simple, just so we can get some appreciation of the limits and fits. So, like I said, 35 millimeter bar, and we're going to go with a H11 hole. So we're looking at this chart like a bus timetable now. H11, so we're going to go down. So the upper limit of this bar can be 36.60 millimeters. That's the upper limit of manufacturing this component. The lower limit is stated below, which is 0. So the lower limit can be 35 millimeters. So the same, so that's for the hole. For the bar is the C11, C11. So we go down on C11 until we get to the range between 30 and 40 millimeters. So the lower limit, let's say the upper limit of that hole would be 34.8 millimeters, and the lower limit would be 33.2. Those two components, they're going to fit together dead easy. When we get right down at the bottom of the chart, that is for a slack fit. As we're going across, you've got a loose fit, which is slightly tighter. You've got an easy fit, a normal fit, close fit, slide fit, a push fit. Then we're going into a drive fit, which means you have to put some force. I'll just get myself out of the way so you can see the others. A press fit, so you'd have to use hydraulic force. And then we're going into a force fit, and with a force fit, you would have to use heat and heating up the hole to expand it out. You would put the shaft then into a freezer or liquid nitrogen, contracting that down as much as possible, with the hole then expanded using like oxyacetylene torches. You know, we're talking red hot. You would then use a hydraulic press them together, and then let them naturally expand and contract. And they are going to be, you'd have to machine them to get them to separate again in the future. So that is the British standards for limits fits. For limits fits on shafts and holes, basically. So that chart, if you want to go into it, or any of your design stuff, quick Google that chart. It's the British standard, and has been since the 1st of February 1970. So it works. So we've touched into this a few times. So thermal expansion when you're machining a component. it needs to be taken into account the atmospheric temperature if you're making components which are very tight fitting. So in this little two little paragraphs that I summed it up with, basically, if you had a component which was made in the north of Scotland in the deepest of winters, and you're measuring it, we'll say a 20 millimeter shaft, and you measured it in the depth of winter and you machined it perfectly to 20 millimeters. Your colleague then was machining the hole for it to go into at the height of summer in Spain. That would have so the whole of the shaft would be very small because of the material temperature, and then the part that was manufactured in the height of summer in Spain would be too big. So number one, using coolant will drop the rate of thermal expansion. Also, if you're manufacturing something to those tight tolerances, you would have a temperature controlled workstation. I'm just trying to give you an example of why you would have to think about temperature in the manufacturing process. We are talking NASA level components being made. Most components would have a tolerance which would eliminate that out of to stop it being a factor. So when it goes into an inspection lab, they are normally temperature controlled to about 18 degrees. They would have the humidity controlled, and they would then, so they would take the component in and it would normally sit and wait for inspection for up to, I've seen up to a fortnight for very large items. But then stay there a day to get to the temperature controlled temperature. Then they are measured extremely accurately with a CMM machine, usually, to make sure that they fit the requirements that were set out in the drawing. So that would also work with the part that I've picked on Spain. So if the temperature was, we'll say 35 degrees in Spain, when the other component was manufactured, it would go into a temperature controlled lab at 18 degrees. It would then contract down and then be measured and to make sure it fits within the tolerance of the drawing. By doing this, then it will reduce the amount of failed parts that are going out. So if a company, for example, was making brake components, they have in some parts that were manufactured in the UK, other parts that were manufactured in Spain, we'll say, we'll go with the same two countries, and we'll say they were going on the left and the right sides of the vehicle. The UK one, you don't want it to be any different to the one that was made in Spain. So that's why they would have temperature controlled inspection to make sure that these parts fit perfectly together and carry out the same function. So tolerances on the diagram. I'm not going to go into this with great depth. You've probably covered it either in high school, college, university. You must have come across this by now. On a diagram, you've got a 3mm, I'm going to pick on this bit here, diameter of 3 plus or minus 0.05. So the upper limit then would be 0.05 above 3mm, giving a total of 3.05mm. Okay, the same goes for all of them, unless it's stated next to the actual component dimension. It would be set out usually at the bottom in the middle section, so that and it would say all components with a tolerance of 0.25mm unless otherwise stated, and then there would be a part on there that would have a different tolerance because it's a tight fit. Angles are normally to 0.5 that we found within educational machining, and then so it would go down to half a degree or 30 minutes of a degree. So following on now, so that's basically the end of the presentation. I've compiled some videos that will assist and build up your understanding of what I've gone through. So we've got this gentleman here. It is an American video, so all the measurements are in imperial. So when he does speak about the measurements, just bear in mind it's imperial, it's in inches. And also, because you've watched the video, don't think that you can use this machine. Get training, because these machines are extremely dangerous. Just want to clear that up. Got this video of a lathe. I will say that these machines should have some form of guarding around them, but without the guarding, it shows the machine in operation quite well, so that's why I've used it. Again, because you've watched the video, you get training before you use the machine. These machines, as I said last time, can kill, so please be careful. There's a very good video on surface finishes. So it explains it in a little bit more depth and a different way to the way I've explained it. So bear in mind, the links should work when you click on them. Failing that, I've written down the YouTube link to have it, so you can, if it doesn't work via the link for any reason, you can manually type it in. Again, another video, limits and fits. It's a very basic way of showing it. All of these videos that I've put together, I use for my everyday learners, and hopefully they'll assist you. Thank you very much. And yeah, it's been brilliant going through this with UWE learners. Stay safe, everyone, and take care.